let's talk about how we go from kinetic energy to work kinetic energy theorem. So look, if we use work, right, we know this, but we're just talking about it from a different perspective. If you apply a force, what do you get? F equals what? Ma. So if you apply a force, you get acceleration. What does acceleration do to speed?
It speeds it up or slows it down.
Changes the speed. Okay, so if you apply a force, you know you're going to get a change in speed. If you have work, that means you've applied a force, which means you know you're changing speed. Okay, so you can use work to change speed. Now, conceptually, this is not much different from what we've done, but this is going to give us some new math to work with. So look, if we have a block here and it slides over here, right, even though we have the same external force, we're going to have a larger speed because this thing is accelerating as it goes this way. All right? So look, we start with an initial speed, we end up with a final speed. What do you notice about those two speeds? Is this speed the same as this speed? No. This is getting bigger, okay? Because we have some acceleration, we're speeding up. All right? If we look at this in terms of work, all right, let's try this out. So let's say we have work. That's going to be F dot dr. Okay? Well, what's the force here? What's force equal to? Mass times acceleration. Okay? So we end up with mass times acceleration, and let's call this dx. Okay? Well, what do we know about acceleration? How can we write acceleration?
That's the derivative of velocity.
Yeah. So let's say this is m dv dt dx. Okay? So now we're going to do something a little bit crazy. Okay?
We're going to factor out the UDT.
Well, we're going to use chain rule. Okay? So look, this has variables of x, so we can write this as m dv dx dx dt dx. Okay? So everybody remember chain rule?
Yeah.
Does that look like chain rule to you?
Yeah.
Some people are shaking their head no.
Look.
Look,
Derivative.
if this,
The DX's knockout.
if you look at this, these cancel, right? You
Yeah.
end up with this. Okay? But we know velocity is also a function of x. You can write this like this. Okay? This is, if you don't know this is chain rule, go complain to your calculus instructors. Okay? So, we have this now. What do you notice about this? What can we get rid of now?
DX.
You can get rid of. You want to do what, the particle?
So let's pull out m because that's a constant. All right. We have dv, dx, dx, dt, and then we still have dx. Okay. So let's pull out the dv. All right. And we end up with m. Let's see. Let's pull that out, and we have dx, dt, dv. Now what is this?
Change
Or
it.
sorry.
Velocity.
V, dv.
Yeah.
Okay? If you integrate this, you end up with 1/2 mv squared. Okay? And this would be from, we can change the limits of integration because over here it should be something like x initial to x final. All right? When you do your change of variables, you can make this v initial to v final. Okay? So you can write this as 1/2 mv final squared minus 1/2 mv initial squared. So that means work is equal to the change in these terms. Now, does this look familiar?
Kinetic energy.
Yeah, this is kinetic energy. This would be kinetic energy initial. This would be kinetic energy final. So this says that work is equal to your change in kinetic energy. Okay? And this means, this is what we call the Work Kinetic Energy Theorem. So here's, if you want to go back through this at home. There. And then you end up with something that looks like this. Okay? It turns out these are kinetic energy terms. Remember, kinetic energy is 1/2 mv squared. Okay? So this says kinetic energy is the energy of motion. Work changes the energy of motion. All right? So this is a definition. This is our definition of linear kinetic energy. All right, there's also a rotational kinetic energy. It's I omega squared, 1/2 I omega squared, where I is the moment of inertia. Omega is the angular velocity that we talked about with rotational stuff. We'll get there, okay? But we're starting here. Okay. So this means that anytime you put work in, you can get a change in kinetic energy. That should make sense. This is what we already know, right? If you apply work to this chair, it speeds up, all right? So this is just saying that if you apply a force, you can change the speed. All right, so just in case you got lost in the chain rule, it's really not much difference from something we already know. Okay, so now that we know what kinetic energy is, people now. We're mostly thinking C. Please discuss. Will vote again.
So it's obviously not A or B because C has a negative dotted sign having zero kinetic energy since its velocity is 0.
And the arrow.
And then yeah, exactly. So it would have the most amount of kinetic energy.
Yeah, A.
And then B and D have equal.
C would
Yeah.
be 0. So you chose C? Okay. Oh no, I thought you said C and A or 0. I was like, fine with the arrow.
No.
No, 'cause it's like,
I mean like ball C is
yeah.
0.
No, I thought you said both C and A. I was like, dude, look at the arrow.
The key is to wait until you really need it. You start to really need it. I didn't do it.
Did you get lost in the chain room over there?
Yeah, just a little. And I was like, wait, oh, that makes sense.
I was struggling to remember, like, oh shit, are we actually going to multiply those out, or do you just want it symbolically? So I was like, dx dt, I was like, fuck, that's velocity.
Couple cups. Yeah.
Oh, did you want
All right.
Yeah.
We are missing 5 people. Vote again. Close enough. All right. Yay!
Whoa!
Of the people.
Have we had 100% before?
I don't
Not
think
often.
so.
So, 1/2 mv squared. All we're looking for is bigger speed means bigger kinetic energy. So even though we know the thing at C still experiences acceleration, we only care about speed. And when I say speed, I don't mean velocity, because remember, we're squaring the velocity, so the direction doesn't matter. So these two things have the same kinetic energy. This has the biggest kinetic energy, and that has no kinetic energy at that moment. Okay? So the answer is going to be C. So this brings us to our work kinetic energy theorem, another deceptively simple equation. Okay? If we apply external work to something, we experience a change in speed. All right? So when work is done on the system, and the only change in the system is its speed, the net work is equal to the change in the kinetic energy. Now, this has to do with the fact that the system doesn't have any like friction or other stuff happening that we're worried about. Okay? All right. So we'll do a little problem.
A 1.5 kilogram model rocket is launched straight up from rest. The thrust from the rocket is 40 newtons. What is the speed of the rocket when it is 50 meters above the ground? Well, first let's draw a free body diagram for this situation. So we have here use our free body diagram. So we have the thrust upwards, and we are also going to have gravity downwards, which we'll represent as mg. Right? We're assuming the thrust is stronger than gravity, and we'll call it F thrust. And so what are our knowns at this point? Well, our knowns are that the force of the thrust is 40 newtons, that the mass is 1.5 kilograms, and that delta y is 50 meters. So that's what we know so far. What equations do we need? Well, we want to calculate, we're going to use basically the relationship between the work, right? Work net is equal to the change in kinetic energy. We're going to use that to find the final speed of the rocket, assuming, it starts from rest, so we can find K final. And we need to remember that the kinetic energy is 1/2 mv squared, and that the work done by a force over a distance, this might come in handy, maybe or maybe not, is force times the distance traveled. So these are the equations that we're going to need. So let's calculate our solution then. So our solution is, let's start by first calculating the net force. The net force is going to be the sum of the two forces on it, right? So we're going to have the force of the thrust upwards minus the force of gravity downwards. And so the force upwards we saw is 40 newtons, and the force downwards due to gravity is 1.5 kilograms times good old 9.8 meters per second squared. And when I work all that out, I get about 25.3 newtons. We're also going to need the net work, right? So work net is going to be equal to F net times delta y. And so that is, we have our two values, right? Our F net is 25.3 newtons, and our distance that is traveled is 50 meters. It goes up 50 meters. And so using that, we can calculate that the work done is 1265 joules. So now we know the work done, and we can use all this to calculate the final speed. So let's use our work kinetic energy theorem, and that is that work net, here, let me write over a little bit here, work net is equal to the change in kinetic energy, or work net is equal to K final minus K initial. Now, since it starts from rest, we can say that K initial is 0. So let's plug in for our kinetic energy. So work net is going to be equal to 1/2 mv final squared, and that's what we're trying to find, is v final. So let's solve for v final, right? Solve for v final, and if you invert that equation, you get that v final is equal to the square root of 2 times the net work divided by m. When I plug in all, so now we're going to plug in our values into here. So if I plug in my values, I get 41.1 meters per second. So that's how fast it is going at the end. And that is our solution to this problem.
Okay. Let's take a break. Okay, problem 2. We have a car that's traveling 20 meters per second. It slams on its brakes and skids to a halt. If the coefficient between the tires and the ground is 0.8, how far does the car skid? So when we read through the problem, we want to look for some key words. Okay, so we have some values that we want to keep, like there's this, let's see, we'll call this a 1,000 kilogram car. All right, we have a speed that's 20 meters per second, and it skids to a halt. So that's actually an implied speed. That means we end at 0. It skids, so we know this is kinetic friction. It's sliding friction. It also tells us that. But we know the friction coefficient is this, and we want to know how far the car skids. Okay? So we're going to start by drawing a picture. And remember, when we draw a picture, we want to make sure to not just include the stuff in the picture, but also to include some coefficients. Okay? So we have a car. Here's my car. It's moving with a V initial of 20 meters per second. Then the little car, over time, slams on its brakes. At this later time, V final, we know we're going 0 meters per second. So we start at x equals 0, and we finish at x final, which we don't know what that is. We also know, so as we slide to a halt, the coefficient friction is 0.8. And one last thing is the car has a mass of 1,000 kilograms. So, to do this problem, we want to write what we know and what we don't know. So we know, we've already done most of this, we know V initial is equal to 20 meters per second. V final is equal to 0. We know that x initial is equal to 0, and we don't know what x final is. We know that the mass is 1,000 kilograms, and oops, is it 0? And the coefficient of kinetic friction is 0.8. So before we go any further, we want to see what kind of answer are we expecting. So we have a car that's going 20 meters per second. So 20 meters per second, that's about 45 miles an hour. And so if you're going about 45 miles an hour and you slam on the brakes, about what range of stopping distances would you expect? I'd sort of guess anywhere between 10 meters and 100 meters. So less than a football field, but not immediate. Okay, so this is our guess. And we're going to move this over here. Remember, we're always trying to make an order of magnitude approximation. So anything between 10 and 100 makes sense. And that's order of magnitude, because that's a factor of 10 difference. Okay, but to solve this, we need work kinetic energy. And actually, because we need work, we're going to have to redraw our car one more time. Because we need forces. So we know normal force, weight mg, and then we have our kinetic friction, which is mu k n. And we know what n is from this. So we're going to use that too. Alright, so to solve this, we need work kinetic energy theorem. So work is equal to the change in kinetic energy. Well, work is made up of, and this is the work external, work is made up of force external, delta x, where this is delta x. It's going to be x final minus x initial. Alright, so just to keep that going, kinetic energy is 1/2 v final squared minus 1/2 v initial squared. We already know that v final over here is equal to 0, so that goes away. What's our force external? Well, this has to be in the x direction. So we know in the x direction we have mu n, and we know that n should be equal to mg. So this becomes mu mg delta x is equal to negative 1/2 mv naught squared. Now where does this negative come from? Well, this is clearly pointing backwards. So this is a negative force as well, and these negative signs cancel out. Once again, we also have mass on both sides, so that's going to cancel out, and we solve for delta x because that's the distance. How far does the car skid? And so then we're going to just solve. So we have V naught squared over 2 mu g. All right. Plug in some numbers. That's 20 meters per second squared divided by 0.8 times 2 times 9.8 meters per second squared. That's going to give us 25.5 meters. Okay, so that's our answer. Does it make sense with what we thought our answer should be? So we'll go back over here and we'll say, well, we're looking for something between 10 and 100. 25.5 meters is between 10 and 100. So that's our problem. Just filling in over here. Remember, this is delta x. And since x initial is 0, delta x is the same as x final in this case. All right. Thanks for watching. Question. Okay. Oh, all right. Please discuss. We'll vote again. We'll take about a minute and a half so you have time to read the whole question.
I guess.
You guys. Okay. Okay. Work equals delta. Okay.
Right, so it'll be.
Okay. Better. So, let's talk about this. So at this point, we start with a kinetic energy of 2 joules. Okay. From a work kinetic energy theorem, we're looking for kinetic energy final. So, but if you have change in, work is equal to kinetic energy final. Oh man, final minus kinetic energy initial. So if we want kinetic energy initial, it's just work plus, final, plus kinetic energy. Did I totally confuse you? So look, this is just work kinetic energy theorem. Okay? So change in K and change in anything is final minus initial. Okay? So if we just solve for the kinetic energy final, which is what this problem's asking for, it ends up being the work external plus the initial kinetic energy. Well, we're given the initial kinetic energy. What is it? 2. Okay? How do we find the work? Area under the curve. Now we need to know our limits of integration, so it says 0 to 4. Okay? So from 0 to 4, what's the area under this curve? 4 joules. Okay? 1/2 4 times 2 gives us 4 joules. So the final kinetic energy, just the energy, it's not asking us for a speed, is going to be 2 joules plus 4 joules. Okay? Do you think this thing's going faster or slower? Faster. We've added energy into our system by doing work on it. So this thing is now going faster. Okay? What if it asked you, let's say it started with 2 joules of kinetic energy at 0 and it wanted to know how much it had when it got to 2. What would our total energy be, final kinetic energy be at 2 meters? Yeah. 3 joules. Why? Yeah, 1/2 2 times 1. The total area from 0 to 2 would just be 1 joule. So it would be 2 joules that we started with plus the external work, which would be 1 joule. Okay? So make sure you keep track of the graph and the limits of integration when you're doing these sorts of problems. All right? Okay. Here's another question. We've got a little of everything. Please discuss. We'll vote again.
The way I chose C, but the way I saw it is that since they move the same distance and then what else? Equal forces were used to move, and then they have the same.
I don't know. Discuss.
Much better. So, good discussion. Look, what's our initial kinetic energy here? 0. Are we moving at all? No, you can't have kinetic energy if you're not moving, okay? So you're not moving, you start with 0 kinetic energy. How much work do we put in? Well, the force is the same. What else goes into work?
The distance is
The
the same.
distance. The distance is the same. So we have the same force, the same distance. The work is the same. So 0 plus the same amount of work gives you the same final kinetic energy, okay? And this is because of the vocabulary. Look, if we were asking about the speed, we know which one's going to have more speed.
The small one.
The small one. Why?
Because it's lighter.
It's lighter, okay? So 1/2 mv squared, to get the same 1/2 mv squared for a 0.2 kilogram thing and a 1,000 kilogram thing, you change v. So that means your v for your toy car is going to be much, much bigger, but the same amount of energy. Okay, you can just do more with it because you have less mass.